Hey everyone, thank you so much for joining the next talk that we have prepared for the Julia Health Mini Symposium. Today we have our speaker Oskar here talking about Cox model Go brrr, a journey to performance. So Oskar, I will turn it over to you to present. Thank you so much.
Thank you. Um, Let me just start my timer. So this is a talk that basically tells the story that happened to me through last year. We wanted to exploit the power of Julia to implement some model, and we had a few issues. So I will try to explain why, and then we'll go on the how and through some of the results. So I need to talk in the mic. Yeah, maybe I can just take it, or you know what? Give me the other one. Is okay. That's better.
Yes.
So I come from statistics, right? And this is a bit of this is an implementation of known model in survival analysis. Survival analysis is a branch of stats that take care about time to event data. Those are data that you get when you study, for example, medicine with people dying. People might die at a certain age, but you might also end up the study before they die. And so there is a thing called censorship in those data that might happen and that need to be treated specifically in terms of stats. This theory is widely used in medicine, of course, but also in engineering for failure of equipments, in economics, and in a lot of fields. The characteristic is the presence of censorship. I'm going to describe what it is later. The field exists as a theory since a while, and since computer came around, there was implementations of it, and most of the state-of-the-art code today is basically in R. And this work, and what I'm doing since a few years, is an attempt to port some of that knowledge into Julia. In R, there is one package that is called Survival, this one from CRAN, that is maintained by Terry Terno, which is at the core of the ecosystem. And it's a 30 years old piece of code. It's maintained since then. And it's very, very important because this is the list of packages that depends on it. So the list is a bit long. And all those guys use the work from Terry Terno, but none of them help him maintain it, basically. The guy is alone maintaining this piece of software that is used by everyone. There is an XKCD that basically applies here. This is the piece of software that we are talking about, right? With one man maintaining it since 30 years. And the guy is going to retirement in a few years. That's also a problem. But why? The question is now why it happened like that, and in fact it's a two-language problem. It's the fact that most of the underlying architecture and the underlying models are written in C and not in R, and those users are used to R and not C, and so they don't contribute because basically they cannot. So in Julia, there wasn't much. There was a few tentative at implementing some stuff around the time, but all of them did die. There was one 2 years ago that we asked if we could take back the package and start from it, and the guy that owns it never answered us. So we started again 2 years ago with this Julia Serve organization that now holds a few packages. So you have a few that are underlying and maybe background. In the base, there are a few standard types. There are a few standard distributions that are used in the field that are not in distributions.jl. So we picked the API and implemented some of the things that we needed with it. There is the rate tables.jl that implements mortality tables, which is an important kind of data that exists in this field. And there are a few ones that are more user-facing. So the first one is from last year about a very specific niche survival problem, which is called relative survival analysis. And the last one, which is the one that I'm going to talk today about, is called survival models.jl, and it provides tools to make regression on survival data. Okay, so let's go to the core. So a survival issue is an issue where we observe some characteristics from several independent patients. Let's say patients because we imagine that we are in the medicine field, but in other fields you might work with lights, for example, that might die at some time. And so we observe T and delta, which are the time to events, the survival time, and delta is the status indicatrix. It gives you a 1 if the person died, and a 0 if the person did not die at the time T. And in fact, those things are constructed from underlying time. So there is a true survival time O that we don't observe, and a censoring time C, and T is basically the minimum between the two, and delta is the indicatrix that T equals O. And on top of that, we have some covariates X that are given, and the goal is, of course, to characterize the distribution of T given X without taking into account the nuisance that is the censoring, the nuisance from C. So we have some kind of filtration that is going on. Across the time, we have more and more information that are coming on. The estimator and statistical procedure that we construct will have properties related to this filtration, martingalité, and stuff like that. The characterization of the distribution of T given X is done usually through what is called the hazard function. You might know that a distribution function, that a random variable can be characterized by its distribution function, by the density, by the survival function, which is 1 minus f. Those things are equivalent, but in survival analysis, we prefer to characterize things through their hazards, which are the negative log of the survival function, or the derivative of it. Why? Because the problem that we have here is a minimum. T is the minimum between O and C, and the hazard of a minimum is the sum of the hazards as soon as we have independence. And therefore, this characteristic function of the random variables are used in survival analysis to model things, because it allows to transform this minimum in the realm of random variable into a plus and faster subtraction, which is easier to deal with. So the Cox model, that is the subject today, was introduced in 1972, and it's basically a log linear model for the hazard function. And so it gives you lambda as lambda 0 of t times the exponential of beta times x, where beta is a vector of parameters to be fitted, and x is the covariates. It has one key feature, which is that the effect of covariates is multiplicative, and it does not depend on time. You see that there is a separation between the variable t and the variable x in the function, and this is what is called the proportional hazard assumption. This is an assumption that is usually false, but this model being old, being kind of the first one to be able to model those kind of things, it's still very predominant in the literature. And when some new data comes in, this is basically the first thing that a practitioner will try. So how does it work? From the lambda function, you can construct the likelihood, and then you simply minimize the likelihood to obtain the parameter. Of course, there is an issue, because this likelihood here has two parameters, the beta and the lambda 0, but with a few hypotheses that are not that much a problem. The proportional hazard hypothesis, in fact, in the main paper, Cox was able to derive some partial likelihood that only cares about the beta, and this is the function that we are trying to minimize here. Yeah, so to minimize the likelihood, we can minimize the log. So if we take the log of this function, we get something that looks like that, where the delta i's here are 0 or 1s. Here you get something that is linear in the beta, and here you get some log sum exp. So log sum exp, there is a numerical warning to be taken here is that the logsumx operation is known to be unstable. And in fact, there is a way to stabilize it, which is to take the maximum out and to remove the maximum from the inputs. Because here, if the AJ are large, the sum will be not very precise, and you'll get imprecisions. But here, the AJ minus the maximum, all of them will be negative, and so this exponential will be small, and this will be much more stable. In Julia there is a package called logx function that does those kind of stuff for you if you want. Okay, so we have a loss to be minimized. So let's go. The first thing that we tried to do is basically one line of code is to take out optimization.jl and to write the loss. So here it's an n meaning the negative log likelihood that you are trying to minimize, because usually you want to maximize the likelihood. So if you take the negative version, you can minimize it. And it writes very easily in Julia. It's completely similar to the equation that is here, which is very nice. And in 2 lines, I have a struct here that will simply fit the model and store the beta as it should. This thing will use automatic differentiation to compute the gradient of the problem and try to solve it. I don't know what is the default. I think the default is probably LBFGS. I don't even check, but it works correctly. The issue is that it's pretty slow. It's in fact very slow because this function here is not very optimized. You see, I did it on purpose, but there is 2 times the x time beta here, which is a matrix vector product. So we are doing it twice. This is not very good. And here there is a matrix I of indicators that is very structured. And this structure can be exploited to do much better in terms of performance. So this is what we tried in the first version, is to implement the derivative by hand instead of having them computed by the automatic differentiation method. And in fact, it's not very hard to do. So you can get out the gradient, you can get out the hessian. And if you take a second to look at it, you'll see that in the gradient here, you have a piece here that is simply the weighted mean of the x's by these w's. And here you have the weighted mean by the w's of the square of the x's minus the square of the means. So this is kind of a variance where this is kind of an expectation. For the moment, this interpretation has no interest. Well, it still has one. The main interest is that this is positive. And since it's the variance, it means that the hessian is definitely positive, and thus the problem is strictly convex, which is a characteristic that we need to exploit if we want to achieve performance. So that was my version 1. Just implement the derivative by hand, give them to optimization.jl, and try to do better. Then I have a version 2, which is exactly the same, but where we tried to remove the type instability that we had. There wasn't that much, but mostly the allocations. And this comes from the fact that implementing the derivative by hand is not an easy task. So we had a lot of allocations in them. And the strategy is simply to pre-allocate those things and then fill them in place to be able to get the performance. And this is something that you might do for other codes too, and there are very good reference online on how to do it. You need profiling tools, so there is the @prof view. You need to check allocation with alloc-check.jl, type stability, etc. So once this is done, and once we are sure that the code is as performant as it could be, you can't do much more. And the version 3 that I have, the next idea that we had was to simply get rid of the optimization.jl and implement ourselves the solving loop. In particular, to have the opportunity to pick very carefully the stopping conditions to be certain that we stop when we want, instead of using some default that we don't control. So this version 3 is basically getting back most of the problem for ourselves instead of trusting optimizations.jl. In fact, while we do that, we can also exploit the convexity as its maximum by using pure Newton-Raphson instead of some Newton with an approximated hessian. So this was also part of the gain that we had here. So we thought that we were at the maximum, but then something else happens. It's that if you look at the hessian here, I told you earlier that it has a variance structure, and in this variance, you can think of it as the variance of a certain random variable, where the atoms of the random variable are known. This is a data set, but the weights depend on the parameter. And in fact, you can bound this by saying that on a known support, the variance of a random variable has a maximum. This is basically the random variable that has weight 1/2 on each side of the support and 0 in the middle. And this is the variance that it has. And so we can maximize the variance and in fact bound the hessian. And this gives us a convex envelope on top of our loss that we can exploit, because this bound can be computed before the gradient descent. And thus, in the middle of the hot loop, we don't have to compute the hessian anymore. We can simply use the bound. So we have the guarantee because it's a convex envelope, and therefore it will converge. But the drawback is that the direction that will be taken by the gradient descent is a bit less optimal, of course, because it's not pure Newton-Raphson. And therefore, this will increase a bit the number of steps that the algorithm will take. And so there is a trade-off between the fact that the steps will be faster, but we will take more steps. And this trade-off has a lot of things to do with the size, the shape of the problem, which is something that we don't control that much. Okay, so there was other versions too, but that's enough. Let's go for the results. What do those implementations give? So first, the interface that we have, we tried to basically copy the interface that is available in R, and we have a simple fit function with a fit of Cox. You put a formula in here and then the data set, and it outputs the results on this form with the name of the predictors, the betas that were fitted, their standard error, some p-value for the test that you should include or not the variable in the fit. And with that, we hope to be able to grab some of the users, because the interface will look like what they are are used to. And our different version can be accessed by telling it which version you want. But if you just say Cox, it will pick the best. So this is a simple test to check convergence. All of the versions were calibrated to have the same convergence criterions. So they basically converge to the same point. And the point of convergence, the loss is decreasing with the number of observations, which is normal. And here you have the runtime, finally, of the different versions. So I don't know if you can see the colors that well, but the two on top are the version 1 and version 2. The most dumb one, this is the version 0, the optimization.jl. So our tries to do better than optimization.jl were in fact not that successful. And then you have the version 4 here in green. And on the way bottom is the version 3, which is our most performant. And the red and the black line here are what R does, the red line. And the black line is what survival.jl, the previous version that existed in Julia, does. And in fact, so the red line is the R line that I was talking about at the beginning of the slides, the one that is optimized since 30 years. And we beat it completely by a factor 10 approximately. So this is very good results. Here you have only the lower ones, the most performing ones, and you see that the shape is basically the same between the two. This is because we use the same algorithm, but our implementation is better. And here you have the same shape too. one important thing to see on these graphs is that the runtime is basically linear in the number of observation here and in the number of dimension here, which is expected from the structure of the algorithm itself, and which is nice to be verifiable. So to conclude, the fact is that with a few lines of code, we were able in a month and a half to beat the gold standard by a 10x, which is a very good result. The gold standard is in C, so we are not competing with our code, we are competing with C code. And we checked that the algorithm that they have is in fact the same that we used at the end, the theoretical algorithm, but our implementation is just plain better. Yeah, this provides also efficient and easy to use implementation of Cox in Julia that were not there before, so it's a step in the right direction. But in the package, in survival models.jl, there is also a lot of other stuff. There are non-parametric models such as Kaplan-Meier, the log-rank test, etc. And there are also parametric versions of the general hazard model, which are over models that you can use. But of course, the field is wide, and there are a lot of other stuff that should be implemented around those models. In particular, the possibility to add non-linearity in the regression through splines or something like that will be very useful to the practitioners that we managed to discuss with. All right, thank you very much. If you have a few questions.
Awesome. Thank you so much for the wonderful talk, Oskar. At this point, floor is open for questions. So if anyone has any questions, feel free to ask. And if you can speak into the microphone, just so.
Sure. Yeah. So yeah, one is time varying covariates. Is that in your to-do? Is that like splines and nonlinearities? Is time varying covariates in there?
Yeah, this could be. Yeah.
And then second question, maybe harder question. Can you replace the underlying C code for R, so R users can use this Julia implementation? What would that look like if you thought
I would love to do that, but I think you have to talk to other people for that, to discuss with the -- trim. There is a talk this afternoon, I think, and the goal is that when Julia will be able to compile into a DLL, .so library that is thin enough, and then we can take this .so, put it into an R package, and ship it on CRAN without them even knowing, which will be much easier than what we are doing for the moment, which is shipping a full Julia into the R package, which is not possible, and so it forces users from R to install it aside. They don't even have the right version all the time, so it's a bit more finicky. But I don't think it's ready right now. Maybe in a year or two. Yeah. But yeah, that will be a huge step forward.
Another question?
Hi, thank you. You seem to have very impressive results, especially compared to the current standards. I mean, you say 10x. Do you have any examples of like applications where this time improvement would be especially helpful, especially since this is like a health mini symposium in that operation?
Yeah. I have a colleague at my lab that is using the underlying optimization routine to do it in each leaf of a running random forest. And therefore the number of times that she has to compute this minimum is very, very large. And using the one from R, she gets runtimes of about a week. And we are trying to use that now, but it's not done yet. But we hope to get improvements, right?
Would you expect 10 times improvement? Or?
Yeah, definitely, because the rest of the code is just moving stuff around. So.
Thank you.
Okay, I think we got time for about 2 or 3 more questions. Any more questions?
Do you have your eyes on any other models that you want to make go brrr?
Yeah. If we just go to survival models.jl, I don't even find it. should be here. There is this thing called general hazard that basically has a hazard structure that is like that, which means the notation here uses h's instead of lambdas, but it's almost the same. There is still the same factor here, but there is another one here, basically. And the beta should not be the same. And this is another category of model that basically encompasses a lot of applications. And for the moment, the version that we have is not very fast. So we have a lot of documentation and runtime and tests, so everything is all right, but the performance is not very good. So we are working on it.
What's the difference in terms of, what's the practical difference between the accelerated failure time model and the Cox model, just like intuitively?
It's just a different specification of the model equations, right? And in fact, there are others. I don't see them. See here. There are other way to specify this kind of hazard equations, and we are trying to do something comprehensive to encompass all of them at once. So the generality is there already, but the performance not yet. And with some of them and some of the way to parameterize it, they have interpretations that are not the same. And for the doctors, it's important to be able to get the interpretation that they want out of the parameters that come out of the model.
All right, I'm actually going to ask a question myself real quick. Kind of similar to some questions earlier, tremendous results, especially compared to the state of the art, compared to, I guess, the last 40 years or so. I'm very curious, so far in your journey with JuliaServe and the work that you've been doing here, how has it been received in these venues where they are still using, say, like survival, the R package, or these other ecosystems? How has been engaging that part of the, I guess, community around survival analysis? How has that looked to you so far?
Yeah, it's a good question. It's been hard because if you don't give them enough, they won't move. Basically, the answer that I have is this is great what you just did. Do you also have the opportunity to do that, and that? No, not yet. I have to implement it. But those guys that are using those models have the tendency to be spoiled because they live in a world where everyone recodes the same thing, so it's very inefficient. But the library is huge, right? And basically, they need a lot of it. So, yeah, that's the answer that I can give you right now. It's that we need to do more before some of them will try to switch.
Okay. Thank you. I was wondering about that because within the Julia Health ecosystem, that's also been something we struggle with. We think a lot about how to bring these sort of users into the ecosystem where it's like we do have these performance benefits, but there's such a plethora of other tools in history, like going back 40 years as opposed to maybe 4 years for Julia Health. That's a tricky problem. I was just curious.
Yeah, and at the beginning we tried. The first time that I tried the thing, we did go for netsurvival.jl, which is implementing some niche of survival analysis with the hope that the people into that niche will be able to move easier than others. And actually that worked a bit more. We attacked a very specific point and this worked and we had people move. But here we are trying to give them the general environment that they need, and so it's harder, right? There are more stuff to do.
That makes sense. Well, everyone, thank you again so much for presenting Oskar. If we can give Oskar another round of applause. Thank you so much for answering the question.